A most wonderful, good after morning. I guess, I hope some of you have missed me a little bit. Have you? How is it working? Does the live stream work all right? Or how is the sound? Is anyone here already? Or am I totally abandoned? It's working. Thank you very much. That's great. So that's wonderful. So we just need to wait a little bit. Good morning, Elizabeth. I suppose the advantage of this is that I get to see the names of students, but then the problem is, of course, I don't see the faces. So either way, it's different. But I suppose we have to make the most of it. Good after morning to you, Bob, Jim Bob. Nice to see you here. And a good after morning to you, Ryan, as well. Katie, hello. Good to see you. We just simply have to make the most of this situation, and I suppose not to panic, because there's nothing we can do about it, and we just simply have to follow the old rule. If nature throws lemons at you, well, make lemon juice. Or even better, if you're a biologist and know a little bit about genetic manipulation, if nature throws lemons at you, try and make apple juice. Or cider, actually. Cider is good as well. When you see that the screen is moving, this is just me, it's not your eyesight, it's just simply I need to check if the live stream is still working all right, and what the lag is, so that I can adjust. So please forgive me for that. Oh yes, and I probably should say that the online quizzes are still open. Okay, yep, good. Interesting. Uh-huh. 12 o'clock. Aha, and I can see 28 people watching. Well, that's not too bad, actually. 29. Hi, cool. That is out of, how many should we have? 250. Oh, well, I suppose it could be worse. Mind you, the stuff that I'm going to do with you today is actually something that one of my final year project student is currently supposed to do at the moment, to analyze. She is interested basically in biomarkers of stress and how stress is linked to heart attacks. And I think that's quite an interesting topic. So can we identify basically which biomarkers in the body there are that can tell us that somebody is really stressed about something, and then does this stress then actually eventually potentially lead to a heart attack? So it would be then very easy to measure these biomarkers and say, well, you are definitely at risk. I hope you are not at risk. You're not too stressed about things. My understanding is that the university will do everything they can in order to make things all right, make things good for you, and hopefully no students will really get disadvantaged. How we are going to do that with the exams, I have no idea. But I think we just wait and see what's going to happen. Actually, we don't have much options anyway, do we? So the numbers of people watching is going up, and that's really good. I'm really delighted to see that. Got 36 people, and I hope the stream is still stable and good. So I'll try that again. I move it a little bit. Yep, so that's working, and I suppose, because I haven't seen any other messages, the sound quality is all right. Is that good? Sound is all right? Yeah, good. Wonderful, yep. Beautiful. Sound is good, can hear well. That's brilliant. Excellent. So let's see if we get 40 people watching on the stream. And then we get, yeah, we've got 40. Hey, that means, shall we get a start? Because the sooner we start, the sooner we can finish and we can have lunch. And that's my usual phrase. So a most wonderful good after morning, ladies and jelly beans. I hope you are all well. Please don't forget to do the online quizzes for BI 308. And, oh, okay. I'm not sure, Katie. Do you think they are more interactive? Oh, maybe we should, well, let's see what the university does. Perhaps we can learn something from this corona thingy bit. Yes, I think more people respond. I don't know whether it is more interactive, but I think people feel safer to respond. Is that? Yeah, people are less nervous about contributing. That's right, Emily. But why? Why? Is that because you feel you are not watched by the peers, or is it just because you are more familiar with typing on your device or something like that? I think I heard that before, but it's really interesting. It's less scary. Oh, that's really, really interesting. I need to think about it. Anyway, let's get started, because I want to do with you two things today. As I announced in my email, I want to do something that you probably have done at school, because that's one of the typical tests that is done at A-level, and I think probably even at GCSE. We want to do a chi-square test. And actually I want to introduce you to two different tests. What we have done last week was we basically looked at frequencies, at counts if you like, and I showed you the binomial distribution. So binomial distribution and how we can distribution. Difficult to talk and speak at the same time. And I showed you how we can deal if we have a ratio. So for example, if we have, let's say, we count 40 people who can roll their tongues out of 100, that means we have 40 who can do something and 60 who can't. And for a binomial distribution, we said we have basically two options when we want to analyze things. But what happens if we have more than two options? If it's not just roller and non-rollers, if we look at different things where we have more options. So, for example, we've done a little survey and we want to find out which flavor of ice cream people like. So let's say we have, let's be traditional. Let's go for chocolate ice cream. Let's go for, let's say strawberry. Strawberry, typical one is vanilla. And let's do one that's more exotic. Let's go for durian. Anyone heard of durian? Okay, pistachio, yeah, but it's too green. Okay, now here, big question, durian. Yes, Ben, you are right. It's the stinky fruit. No, it's not the vomit fruit. Worst smell in the world. No, I don't think it is the vomit fruit. I mean, it's a little bit like Marmite, because the durian fruit is indigenous to Southeast Asia, and you either love it or you hate it. It has a smell like a combination of fermenting garlic, rotten cabbage, and unwashed socks probably, and the taste is pretty similar. And there are people who absolutely love it, and other people, most Westerners for example, find it difficult to stomach. I'm lucky enough I can eat it, but it definitely isn't my staple fruit. But I know some of my friends really would do anything to get durian. So, and there's also some ice cream, which is interesting. So, let's say we ask 100 people which one they prefer. So let's say we have 50 people who prefer chocolate. We have 25 people who really like strawberry, 20 people who go for vanilla, and let's say we have 5 people who like durian best. Weirdos. Let's check. Yes, we've got 100 people here. And now we want to ask the question, is there a preference? And of course, I mean, we would say, you know, obviously there is definitely a preference for chocolate, which I think is perfectly reasonable. I'm not asking you guys what your preferred ice cream is, because I've seen already some pistachio. Mine actually is a sort of a combination. For me, the bestest combination is lemon and chocolate together. So first, if you have an ice, a cone, you have to have chocolate first, and then on top the lemon, because you have the sweetness of the chocolate mixed with the sharpness of the lemon. And I sound like Greg Williams from MasterChef, but I don't care. That's really for me, that is going to do it. So here's a little secret if you want to bribe me. Anyway, so what we want to find out is whether there is a preference within this data. And you probably can see, yes, people like chocolate, but let's do it systematically. What we want to do is we want to figure out, yep, I think there are some, there's some consent here. We want to figure out what would we actually expect. These are sort of our observed numbers. These are the observed numbers. What would we expect in terms of numbers if we said there was no specific preference? So we can, in a way, we can record expected if no preference was there. And what we can do is we can compare the observed data with the expected data and say, are they in line with each other? So in a way, we can already say, we can formulate a null hypothesis where we say the observed numbers are similar to the expected numbers. And we say basically there is no statistically significant difference between the observed result and the expected numbers. And the expected numbers, or we can also say, when we say we try to figure out the expected numbers, we say we have a sort of almost like an idea, a model underlying. So if we say there are no preferences, what we can do is we can say, okay, we've got 4 choices, we've got 100 people. So what we can say really is we just take 100 divided by 4. That gives us 25. And if there's no preference, we would say in this particular model, we would expect 25 to like chocolate, 25 to like strawberry, 25 to like vanilla, and 25 to like durian. So what we can say here in this case, there's no statistically significant difference between the observed result and the assumed model in this case. And what we assume here is that we have, if you like, we have what is called a uniform distribution. So uniform distribution, it means there is no preference for anything like that. We come across uniform distributions in other contexts. For example, if you roll a dice, you would expect that each number comes up with the same frequency. So for a dice, the uniform distribution would be 1 over 6, 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 and 1 over 6. And if you roll the dice several times, say 1,000 times, if you've got the time for that, you hopefully will see that these numbers, that the frequencies with which points come up, will be close to this expected numbers, to this uniform distribution. But it could also be that we say, well, we expect a different model, and we can then test this model with our chi-square. So, for example, if we are looking at, for example, genotypes with a heterozygote cross, we would usually get 3 different genotypes, and we then can say what would we expect in this case. So this would not be a uniform distribution, it would be a 1 to 2 to 1 ratio. But again, we could very easily test that. So how do we then formulate our alternative hypothesis? Well, very simple. Observed numbers are not the same as the expected numbers, or they are not in line with our assumed underlying model. And what we basically need to do is we need to calculate a test statistic. In this case, it is called the chi-square statistic, like that. It has a particular distribution. And then we compare this chi-square value with a critical value, and if our chi-square test value, so this is the test value here, is larger than the critical value, so if chi-square test is larger than the chi-square critical value, we say it is unlikely that our observed data match the expected data, and therefore we say we can reject the null hypothesis. So how do we do that in practice? So the chi-squared test statistic is simply the sum of the observed minus the expected numbers squared divided by the number of expected values. Right, so that's straightforward. Now let's just simply see how we can do that. What I'm going to do is I just delete this bit here, and then I can write on that so that we see the numbers. Okay, so we said chi-square equals the sum of observed minus expected squared divided by expected. So for the first one, for the chocolate, we have 50, that's the observed, minus 25 squared divided by 25. That's our expected number. Plus, that's the sum symbol, plus for the strawberry we have 25 observed minus 25 expected squared over 25, plus vanilla 20 minus 25 squared divided by 25. Last but not least, durian, 5 minus 25 squared divided by 25. So, the first one here, we've got 25 squared divided by 25, plus 25 minus 25, that's 0 squared divided by 25. That will be easy. Plus 20 minus 25, that gives us negative 5 squared, that gives us 25 over 25. Plus 5 minus 25, that gives us negative 20 divided by 25. So negative 20 squared, that's 400 divided by 25. And this gives us here 25 plus 0 plus 1 plus, and if my maths is correct, then this gives us 16. So we add this together and we get a chi-square value of, chi-square value is 42. And that is actually quite a large value, I can already tell you. Now we need to figure out what this value actually tells us. What does this value mean? So we've got a chi-square value is 42. Now the chi-square distribution is a little bit funny. So we would have a chi-square values here, and here we have sort of frequencies, because it depends, the chi-square distribution really depends on the number of choices that we have. So here we've got 4 choices, and depending on the number of choices, the chi-square distribution looks different. So if we've got only 2 choices, our chi-square distribution would look like that. If we've got, say, 3 choices, our chi-square distribution would look like that. If we've got more choices, we will get something like that. And if we got loads and loads of choices, it will become closer to a normal distribution. But what we are trying to do now is really, we say we need to pick the right distribution, and I'll show you in a minute how to do that. And then we say, okay, we've got our chi-square test value. That's our chi-square test value. And we ask, what is the area under this curve here? And it is, if you look at it, it is on the right side. It's on the right-hand side of the of this curve. And this tells us what is the probability actually that we find this test value or anything larger. So probability that we get this chi-square test value or something even more extreme. If we assume that our model, if we assume that the model is correct, so that we have this uniform distribution. And luckily, the really nice thing is that in Excel you can very easily deal with that. So in Excel you use the equation chi-sq, that stands for chi-squared, and then we want the distribution and we want the right tail. That's the right tail here. And it will ask us for the chi-square value, so chi-square, and in our case this is 42, like the answer to life, universe and everything. And then it asks us for the degrees of freedom. Degrees of freedom. And that is something that a lot of people find quite challenging. What is meant by degrees of freedom? Well, let's say we have 100 people here. So that's the fixed number. How many of these tests do I need to, how many choices do I need to cover so that I get my 100? Sounds a little bit abstract. So I need to ask people, if I have these 4 choices, really, I need to ask people, do you like chocolate? No. Do you like strawberry? No. Do you like durian? No. So I know that this person likes vanilla. That means I basically have to ask 3 questions here. I have to find out the numbers for the chocolate, numbers of strawberry, numbers of durian, and the last number will come by default because I know that I've got 100. So what we have here is really 3 degrees of freedom that I have. So here we would have 3 degrees of freedom, that's the number of choices, plus 1. Sorry, that's the number of choices minus 1 that we have here. Or in other words, I need to determine the numbers for 3 of the choices and the 4th one will come. So let's try to do that. Let's calculate in Excel. So in Excel we want to calculate that. So we put in equals chi-square, and it comes up distance RT. So we had 42 and the degrees of freedom was 3. So let's calculate the p-value for that. The p-value is, oh, that's really, really low. So let's write that down. So the p-value, when we do that, equals 4 times 10 to the minus 9. So this means the probability that we get, this chi-square value with the assumed model, the uniform distribution, is 0.0000000 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's really, really small. What does that mean? It means, well, our null hypothesis is most likely not correct, which means, since we get these values, we have to say our assumed model, the assumed model of a uniform distribution, is not correct. And therefore, we probably need to come up with a slightly different model. We can say, for example, we assume that the majority of people like chocolate and hardly anyone likes durian, and then we can formulate a new model, and from this new model we can calculate new expected values. I think one of the questions in one of the quizzes is what about degrees? Is there a difference in the preference for degrees? So what you can do is you can just simply say we've got 100 people on a biomed degree and we have 50 people on biology and we have 30 people on a biochemistry degree, something like that. And you can say, right, is there any preference? So again, you can do a uniform distribution. You can say, right, if it was a uniform distribution, this gives us 180. I have 180 students. If it was uniform and there was no preference for it, I would just simply do 180 divided by 3. So we would expect 60 students for each if it was uniform and there's no preference. And hopefully that will help you to calculate this chi-square value and also a p-value for that. Is it likely that we get these numbers here if we assume a uniform distribution? So that is how you would address the question in one of the quizzes. Are you happy with that? Does that make sense? Excellent. Please. And I guess you have done that at school, haven't you? At A level. Okay, good. Excellent. But I think not everybody has done A levels. Am I right? Not everybody has done maths A level. Correct? Good. Aha. Ah, that's interesting. So you had to decide a significance, yeah. Excellent. Good. So most people have done that. Now, this test that I just showed you, this is also known as the goodness of fit test. Goodness of fit just simply because it checks out how well our model actually fits. And if we have a cutoff, and we can define this cutoff, and Emily is just asking that question that I wanted to say, so brilliant, thank you for reminding me. We can set a cutoff point, and this again would be the alpha, the significance level, alpha significance level. And we can set that wherever we want. This is basically the cut-off point where we say, right, we make our null hypothesis go. So very often we would set alpha to 5%. And then if we say if p is larger than alpha, If P is high, H naught can stay. And of course, usually you would be given this significance level to make this decision. But if you are then doing your own research, you are of course at liberty to choose a significant level which suits you. So usually it is set at 5%, but you can also set it to 1% or even lower at 0.1% or something like that. In any case, with a p-value that is that low, we would probably always say this p-value is definitely much smaller than our alpha, and therefore we would always reject our null hypothesis. Happy with that? Excellent. Now let's do a slightly different chi-square test. Not a goodness of fit, but a chi-square test for independence. And the best way to explain this test is, and I'm not making any reference to the current situation, the best way to explain this test is, let's assume we have a virus pandemic. And of course, it bears no relationship to what is happening at the moment. And we find that people with a certain blood group, a certain blood type, recover or get the disease in a more severe form. Get disease in a severe form. And I think that ties in quite nicely with the BI 307 practical that you're currently doing. Is that right? You're doing something about blood groups and antigens and things? So, let's see what we have. Let's say we have a group of people with blood group A and blood group 0. And we say here we have a mild form and here we have a severe form of the disease. And we look at people and sort of record how many people have the mild form when they have blood group A. So we have 500 people with blood group A with mild and 300 people with blood group 0. And the severe form, blood group A has 50 and blood group 0 has 10 people with the severe form. What we want to know now is there a link between the blood group and the severity of the disease? And what we can do is we have actually built what is called a 2x2 matrix. 2x2, and it's sometimes called contingency matrix. Contingency matrix. 2x2 because we've got 2 columns and 2 rows. So, have you done that in A level? Anything like that? Yeah, a bit. Okay, good. Some people say no. Okay, good. So excellent. Then it's something new. And again, we can use actually a chi-square test, but we need to figure out what are our expected values. We have our observed values, but we need to figure out our expected values. So, how are we going to do that? Now, the easiest way of dealing with something like that is if we calculate what is called the marginals. The marginals are just simply the sums of the different columns and rows. So the marginal here in the first column, 500 plus 300 gives us 800. In the second row, 50 plus 10 gives us 60. And together, this gives us 860. This is also referred to as the grand total. Now let's do the rows. 500 plus 50, so that's another marginal, that would be 550. And 310, that gives us 310. And we can do a quick check. 550 and 310 also gives us 860. So all is good. So these are the marginal numbers which we will use to calculate actually expected numbers. And what we can already say is that the percentage, so the percentage of people with blood group A, we can easily calculate that. That would be all the people with blood group A divided by the grand total. So that would be 550 divided by 860, right? And if you put that in a calculator, I think you get something like 64%. This, of course, also means percentage of people with blood group 0. That's the rest. That is 310 over 860. And that must be 36%. Because we haven't got any other blood groups, but we could add them and we could do the grand total. Now, what we can say is, of those people, of those with the mild form, and we have 800 of those 800 with the mild form, 64% have blood group A. Does that make sense? That's the, of those with the mild form, that's these 800 here. And we know that of all the people, 64% have blood group A. So we can say 800 with a mild form, 64 have blood group A. Therefore, we can say what is 64% of 800. And if we do that, we find that this would be 512 people. So we would expect 512 people have blood group A and mild form. And that is already one of our expectations here. So let's draw just simply our expected contingency. Mild, severe, 0, And the trick is our numbers here, they are the marginals are exactly the same as we had before here. So 550 and 310. So our marginals are exactly the same as we had. Now we have the expected number is for A with the mild form is 512. And this actually, if you think about, this is the only number that I need for that, because this is from this number, which I need to calculate, I can now calculate all the other numbers. So 512, how many of A have the severe? Okay, give me a number. How many, what do I need to put in here? Where the star is, where the asterisk is. That was easy, wasn't it? 38. I'm not going to ask you because it's really trivial, but you're absolutely right. 512. How many of the 0 have the mild? Well, that's 800 minus 512, and I think that is 288. Am I correct? And the last one is 38, that is 22. Am I right? Yep, excellent. So we had to calculate only one value, and the calculation was pretty trivial. We had to calculate only one value, and all the other values were followed basically without any problems. What about class? So what we can say here, we had only one choice with the A, and therefore our degrees of freedom in this case is only one. If we have chosen one, like this one here, then all the others follow. So we already have a degree of freedom of 1. So let's keep that in mind. And what we need to do now is we need to calculate now the differences. And I'll probably write down the previous ones, so make a bigger grid. So we have 500 minus 512 for the first one, and then we have 50 minus 38. We have 300 minus 288, and we have 10 minus 22. So these are now the differences. So these are the observed and these are the expected. Observed, expected, observed, expected, observed, expected numbers. So what we do now is, again, we do our chi-square equals the sum of the observed minus expected squared divided by expected. So we get 500 minus 512 squared divided by 512 plus 50 minus 38 squared divided by 38 plus 300 minus 288 squared divided by 288 plus, and I'm running out of real estate, 10 minus 22 squared divided by 22. And now the nice thing is the difference is always 12. Good point. I like that, Bob. No, it would not have changed anything, because actually you can try that yourself and try and figure out what happens if we say, for example, we go for blood group 0. So we know we have 36% of 0. Let's say we look at these of those who have the severe form. Let's say of those who have the severe form, that is the 60. Of those 60 who have the severe form, 36% are 0. And you will find that we get exactly the same numbers. So it doesn't matter which one we take, we can do it for everyone, for everything. But why would we? Because one calculation is enough. Does that make sense? So let's go quickly to the calculation. We have 12 to the power of 2, that gives 144, divided by 512, plus 50 minus 38, that gives 12 squared, 144 divided by 38, plus 300 minus 288 gives 12 squared, gives 144 divided by 288, plus 10 minus 22 gives 12 squared, 144 divided by 22. And I think I've done that somewhere. So that would give us 0.3. I just round brutally, plus 3.8 plus 0.5 plus 6.5. So we add them all together, and if I have done that correctly, that would give us a chi-square value is 11.1. That's our chi-square value, that's the test value. And now what we need to do is we need to say, right, we have a test value, chi-square value, with degree of freedom, and our null hypothesis would be H null, observed match the expected data if there is no dependence of between, let's say, between blood group and severity. Alternatively, H1, our observed data do not match the expected data. So basically, our model is here that we assume that there is no dependence between blood group and severity, whereas in the alternative model, we assume there is a dependency. So we calculate the p-value, and if the p-value is larger than alpha, we say if p is high, H naught can stay, and we just simply said a good question, Richard. Answer is more complex, and I might come back on that in a separate tutorial, but for the time being, let's assume there is, there are conceptual differences. So that's all I want to say. Shall we set alpha as 0.5 or as 0.5, which is 5%? Yeah, we do that. So if our p-value is higher than 0.5, we say, okay, we assume there is no dependency, that the severity of the disease is independent of the blood group. Now let's go back to our Excel and let's do the calculation. Equals chi-squared dist RT. We had a chi-square value of 11.1, and we have degree of freedom, we said 1, because we need to calculate only one of the cells, and the rest follows. So what do we get for the p-value? We get a p-value of 0.000, well, let's round it. It's 3 zeros. So p is 0.0009. .05. You are absolutely right. Now it is 0.005. Still, this is much smaller than our alpha, which, as Vena, thank you very much for pointing that out, is 0.05 in this case. So that means we can boot out our null hypothesis, and we can say, actually, we accept the alternative hypothesis, where we say there is, and instead of dependency, I can also say there is a link between blood group and severity of the disease. Naturally, if you just looked at the data that we had here, 550, 310, would you have guessed that? I'm not entirely sure if you could just simply see it from the data like that. But when you do this, test for independence, then you very easily get a reliable measure whether there is a link between things or not. Does that make sense? Are you happy with it? And now I let you into a secret. I actually had prepared this section on the test for independence with the example of our cat, of Gigi, because there is something really weird with her. Gigi, let me see if I can find a picture of Gigi. Let's see. There's too many emails. And no, where's it gone? Yesterday. I need today. Yeah, this is a picture of Gigi. She's really cute. But there's actually an interesting problem. Does anyone know what is special about Gigi? Apart from the fact that she lives behind the curtain or on the windowsill and every night she falls off, and you can hear the ow when she falls off the windowsill, usually at around 9:30. And I told you already sort of what is special about her. Any ideas? Yes, Emily, you are absolutely right. Gigi is a female and she is ginger. And I have nothing against ginger females, but for a cat, this is unusual. It seems that the combination of ginger and female, there is an evolutionary disadvantage. We don't know what it is, but they seem to be less viable as, for example, male gingers. So there is definitely a link between the fur color and the gender of the cat. And there would be normally tortoiseshell, exactly. Interesting is that the fur color of a cat is actually not genetically determined. It develops through environmental cues during the pregnancy of the mother. So that's quite interesting and it's quite complex. The reason why I haven't chosen this example and why I chose the virus example is because last night I read an article in the scientific news where people actually looked at a certain virus that's currently going around the world and it's linked to the blood groups. And what they found is, with exactly something like that, that apparently people with blood group A are more susceptible to catching the virus than people with blood group 0. Whether or not it's more severe, I don't know because I haven't followed that. So I don't know. And as far as I know, Emily, fur color in cats is not X-linked. There is a component to it. So you would not get albino cats if both parents were non-albino. But as far as I know, there is a very, very strong environmental component in the womb, and probably sort of the what dictates the phenotype of the cat is the environment in the womb. But I think that is rather complex. So I hope you enjoyed that, and you now know how you can do a test for independence. Oh, if she's getting even more ginger, well, actually, I don't know how to answer that. I mean, in case of Gigi, we got her a sort of as a rescue cat, and that probably also explains why she has a lot of sort of mental issues. Apparently, her previous owners were extremely cruel, and I think that's quite upsetting because they kept her on a diet of black tea and Jaffa cakes, and I think that is not a good diet for a cat. So we now have to hand feed her. She would not eat any cat food. She only eats brown rice with chicken. So hopefully we will get a good supply of brown rice and chicken. Otherwise, we probably have to eat her. But then there is not a lot meat on her, so we better not do that. And before I talk even more rubbish, I think I just simply stop now. I haven't sent out any emails. I noticed I haven't sent out any emails what we are going to do next week. I might do that tomorrow, but at the moment I simply don't have a clue. So all I can say is thank you very much for watching. I hope you enjoyed it, and I hope to see you in one form or another in person soonish, but God knows when. Just, stay safe and stock up on toilet paper. Take care. Bye bye.